So today we're going to work on thermal expansion, okay? And we're going to get into the area of an actuator. And so on Thursday, I'll give you an assignment to do over the weekend, over the next 4 days before we meet again. And this assignment will be to design a thermal actuator. Okay, so let me show you what the thermal actuator looks like. It's a very simple structure. So here's like a top-down view for it. It's a microstructure. It looks like this. And then it's connected to two bonding pads. So these two pads right here are anchored, and you take this and apply a voltage to it, positive, negative, and so you're sending a current through this material. So this right here is free to move, okay? But because this is conductive silicon, polysilicon, you're able to send a current through this. It goes around this path, comes back down like that. Now, if you send current through a very a resistor with a very small cross section, what happens is that material is going to heat up. Okay, so the kind of dimension we're talking about is like this dimension right here is going to be around 2 microns. Okay, and this beam right here is called the hot arm, and this is called, of course, the cold arm, right? And because this is experiencing a wider cross section as a current goes through here and through here, since you have a higher cross section, then you have less current flux going through this side. Okay, the total current is the same, but the flux is different. Okay, and it comes through here. So this small part right here does heat up, okay, but it contributes less expansion. So what's going to happen as this beam heats up, it's going to expand this direction. This beam right here, it wants to elongate. This one does want to elongate a little bit. It is receiving a little bit of heat from this side over here, okay, but there is an air gap between those two. But they still call this the cold side, and so it doesn't experience that much thermal expansion. So you guys could probably guess what's going to happen as you send current through this thing. It's going to, well, let me ask you, which direction is this going to bend, to the left or to the right? Yeah, it's going to be in this direction, to the right. Because, as you guessed it, this side will expand more than this side. If this side expands, the whole thing's going to bend over. Okay, and so that is a thermal actuator. Some people, what they've done is chain a lot of these together, where you have another copy one of one right here, another one right here, another one right here, and then they have a beam that connects each one together. So you're sort of like magnifying your force. And it's a pretty substantial force that is caused by that. Another type of thermal actuator that's very common, some people call this a chevron actuator or a V-shaped actuator. It looks like this. Very thin beam. And then coming down this way like that. And then it's attached to a bonding pad. Okay, and so what happens is when you send a current through this, right here through this voltage, these will thermal expand, but because they're beginning with, it's pre-bent, it has this angle right here, the whole thing bends up like that, okay? And you can have several of them, again, to magnify the strength of your deflection. It doesn't increase your deflection, but it does magnify the force that you're applying if you're pushing on something. Okay, so basically all of these are connected together. And so you're seeing a current to this side to over this side, and these currents will heat this thing up, and they'll deflect this direction. So what's interesting about both of these is that you can optimize the deflection per voltage that you put in by changing the gap space. You can modify the gap space. You can modify the width of the beam, right? You can change the length of this. So let's say instead of having this length, let's say you want it to be a little shorter. So you have this part come down here instead. And so that's something that you guys will play around with after Thursday. And then you'll try to play around, change the parameters, and try to optimize this type of structure. The structure right here, well, this has a certain angle. And then the question is what angle is this optimized at, right? If the angle is 0, what you have is a beam like this, right? 0 angle. If I were to heat this beam up, and this beam tried to thermal expand, what do you think would happen to this beam? Yeah, exactly. It may buckle. And of course, you don't know which direction it's going to buckle. It's going to buckle up, down, may buckle out, outward or inward. You have no idea what's going to happen. Now, like I was saying, there is an optimal angle for this, where if you have the angle too small and send that apply the same voltage, it doesn't deflect as much as the optimal angle. And if it's too large, it also won't deflect as much. But like for example, here's a picture of a large angle one right here. So for this one right here, very large angle, right? This is not going to deflect as much as this one because of that. So you guys can play around and figure out what the optimal angle is. It's actually quite small. You might be surprised how small the angle needs to be to get the optimal deflection for a bolt coming out. Okay, so let's look at this thermal expansion of the beam. Okay, so let's talk about a beam here. Okay, and let's say this beam is of length L. Okay, sending a current through this beam by applying a voltage across this, you're going to have current and Joule heating, and so it's going to heat up. It's going to increase by some temperature. And the question is how much will it elongate? Let's say it's anchored on this side over here. How much would that elongate? Let's call this lengthening delta L. Okay, so you can say delta L this right here, some of you may know that this is equal to the strain, right? And that is equal to alpha times the change in temperature. And this is the coefficient of thermal expansion. That's the change in temperature. Okay? And the change in temperature is equal to the new temperature minus the reference temperature where it started from. Like for example, if you started from room temperature and you went above that, it would elongate. If you went below that, it would actually shrink. It would shorten, and you'd have a negative change in L. Okay, so that's strain. And also, some of you may recognize this equation right here, the relationship between Young's modulus and stress. Okay, so here's the strain here. Here's Young's modulus. Here's stress. And the stress is the pressure that's applied here. So this is like the force, the equivalent force over that cross-sectional area, the pressure or that stress right here. And so this is what's happening right here. Effectively, when this thing elongates, it's applying an effective force in this direction, right? And for beams, you have let's put it in terms of force here. Force equals the Young's modulus times the cross-sectional area A, which is this right here, SA, over L multiplied by its deflection x along the axial direction. Okay, so we already know that force is equal to force over A is the strain. I mean the stress here. So if you divide this by A and divide that side by A, that A goes away, and so the stress here is EL times X. Then you can back out of it what change in temperature took place to elongate that. Okay, so this is basically like quick hand analysis of this situation. When we model it in COMSOL today, we're going to do a little more complicated analysis. That's hard to do by hand, right? And we're going to send current through there because that's the realistic thing. This, when I talked about this, the temperature, the change in temperature, this right here assumes what the average temperature is along the entire beam. Here, what happens is that this bonding pad is attached to the substrate, so the temperature here is going to be very different than the temperature here. So the hottest part of this will probably be, somewhere around here as the hottest part. It'll cool down a little bit and come around this side. Okay? And your simulation is going to figure out where's the hottest part of this. And of course, you have to make sure that the current you're sending through doesn't make it too hot, such that it causes it to melt. It's melting temperature. You want to make sure that doesn't happen. Some people do that intentionally, where they'll make something really small. They attach beams to certain things just to hold it down so it can survive the fabrication process. And then once they have where they want it, they send a current through to actually sever that beam. So the analysis we do today, it will enable you to determine the temperature at every single point of that, and they'll enable you to determine the deflection that took place, and also, like I said, you guys will be able to play around with the parameters. So that's an idea of the assignment that we'll have. I'll give out on Thursday. For today, what we're going to do is model. It's the same type of physics, but it is applied to a different type of structure. So the structure looks like this. So it's just a simple beam. I'll try to make it in 3D. You guys can see what I'm talking about here. So it looks like this, and you're going to put a voltage across that, and you're going to send current through this right here. And what's going to happen is that this has, it's going to experience thermal expansion, right? And because of that, this beam is going to do something that's similar to buckling. I wouldn't really call it buckling, but it is going to bulge out. And it's going to preferentially bulge out this direction only, upwards. And it's because there's a moment arm associated with it because it's attached to this. So you'll be able to determine what the temperature is all along this right here, and you're able to see the deflection. But this example of what we're doing today is you're going to apply the same physics to a different geometry. The only difference here is geometry. instead of applying a voltage to this stuff, you're going to be applying your voltage across these paths, or in this case, across these paths instead. Okay. So, how's it going? Oh, okay. So, does anyone have any questions about any of this stuff over here? Thermal expansion. It is using multiple physics, right? It has structural mechanics, right? It has thermal expansion. It has current. You're dealing with current as well. So electromagnetic. Thermodynamics, and also structural mechanics. So 3 domains. Start up ComSol if you haven't done so already, and so let's go through this. And a few interesting things that we're going to learn how to do here is this geometry right here is going to be kind of interesting because we're going to learn how to make this geometry by making 2D models. I mean, we're going to take two 2D geometries, extrude them, cross them together, and then just keep the intersection. Okay? And those geometries are this right here. Is this geometry? So this is like one 2D geometry we're going to keep. And this is the same thing, like if you were looking this direction from up above, like that, that's what you would see. Okay? But if you extrude it, then it's just, a block that doesn't get this. But then we're going to have this other geometry that looks like this. So this is another 2D geometry. And that's like looking this direction only into the board. And that's what you would see. We extrude that. We take this, put it right on top of that after doing the extrusion, and then we do the intersection, and then we get this structure, this 3D structure. So that's another really interesting way to make 3D structures, looking at different angles, orthogonal angles, and then do the intersection. So that's something interesting. Another interesting thing is, okay, we can do our geometry freehand, but we're going to use vectors. We'll basically we're just going to put in the points there, and it's a lot of them. So you'll see that, and yeah. Then we'll look at the analysis when we're done. We'll look at how the temperature is scaled. We'll plot the displacement. Yeah. Okay. So let's get started. So go to Model Wizard. And this time we're going to click 3D. Even though we're starting off in 2D, you have to click 3D because you're going to end up in 3D. So click 3D. And then go to Structural Mechanics. Expand that. Go to Thermal Stress. Expand that. And go to Joule Heating and Thermal Expansion. Okay? And then click Add. Okay, now go to Study, down here, click that, and we're going to do Stationary Study this time, and then click Done. Okay, so here we are. So the first thing we want to do is define some parameters we're going to use for our model. So there's going to be initial voltage, initial temperature, and some external temperature that's far away. which is our reference temperature. And also there's a heat transfer coefficient that we have to worry about. So click on parameters, this opens up, and let's start keying in this stuff right here. So V0 is going to be the voltage expression, and you tab over, and then you pay, and then that's going to be 0.2 volts, and in your brackets you put capital V for the units. Okay, and that's square brackets. The next thing is your initial temperature. So T0, tab over, and that's going to be 323 Kelvin. So 323, and in the square brackets, put capital K for Kelvin. And then for your external temperature, put capital T in external in lowercase, and then you put 298, and that's going to be in Kelvin as well, capital K in square brackets. And for the last one, we're going to put our heat transfer coefficient. So that's going to be lowercase k, and that's going to be 5. The units are kind of weird, okay? But it is watts divided by, and then you have to put these in parentheses, meters squared, and then times Kelvin, and then square brackets. So it's watts per meter squared Kelvin. Okay, and that's going to be our heat transfer coefficient. And in fact, remember what we had before, we could type in as a reminder what this is. So our heat transfer coefficient, here's our external temperature. Here's our heat sink temperature. This is going to be the temperature of where this is touching the substrate, right? So the substrate is going to be like, this temperature reservoir, but that's going to be the heat sink temperature of the substrate. And these are also going to be the substrate. Everything else is surrounding it is the ambient. And this up here, it's the applied voltage. What was that? Yeah, this right here is lowercase k. Is that the one you're asking about? Yeah, so this right here is the heat transfer coefficient, and that's lowercase k. All the k's in here are capital K because they stand for Kelvin, the unit for temperature. So for the unit, you have capital V, capital K, and this one right here is watts per meter squared times Kelvin. Watt is capital W, meters, lowercase m, and then you have to square it. So you're going to have the caret or the hat to square it, and then times K, capital K for Kelvin. So that's what you guys should have for this. Okay, so those are our initial parameters. So the next thing you want to do is go to geometry, and to make things easy for us, instead of always dealing with meters, change your geometry. After you click on geometry, change it to microns. And that'll mean that all the plots will show up in microns, and all the entry data points will be in microns. We don't have to put like E-6 everywhere. Okay, then go to geometry again, and then right-click on geometry, and then click on work plane. So we're gonna have two work planes. Here's the first one right here. So you click on work plane, and then this pops up. And so for this right here, go to the plane geometry. So this is it in 3D, but we just want to see the plane that we're going to work with. And as you can see here, it's in microns, micrometers, which is good. And so go over to plane geometry and then right click on it. And we want to enter in a polygon. Okay? That's that first structure. We're going to put this in first. Okay, so we're going to put it in by coordinates this time instead of, I mean, we could just draw it, but we're going to put it in coordinates just to give you guys different flavor. We're going to put it in terms of points, vectors, okay? And we're going to put in all the x coordinates and all the y coordinates, okay? But the coordinates are kind of weird, right? So basically, we're going to put it in pairs. Like if you have x and y, we're going to have x1, y1, and then x2, y2. So they're sort of like this. This creates one segment from here to here. Then we're going to have another pair, but this next pair starts off from x2, y2. Okay, so x2, y2, then to x3, y3. Right? And this is like another segment. And because these 2 points are the same, they're connected right there. And that's how we're going to make our segments. So you'll see lots of points, repeat. So you have here to here, and then here to here, and then another segment going from here to here. You see what I'm getting at? It's like that all the way around. Same with that, except these are curved. It's not an accident for my penmanship. These are actually curved. We'll make these a fillet. Okay, so here's what I better write down what you put in because you guys probably can't see it. So I'll put in these coordinates over here. So for x, you put in 1, 0, put in 2 5s, you put in 2 18s.
Comma separated or?
You can, if you want to. Yeah, spaces are fine. ComSci will take spaces or commas, however you like. And then you put in 4 23s. So you guessed it. This right here is 23. Okay? That's 23. So that's why there's 4 of those. And 2 18s. I'll break these up to make it easier to see, I suppose. And 2 5s. And 3 0s. Hopefully you guys can see that. That goes in the X entry point. For the Y entry point, for the right entry, we're going to have 1 0, 4 1.5s, and if you guys want, you could probably copy and paste. Like once you type in one of the 1.5s, you highlight it, Control C, and then do Control V 4 times. Hit the 4. 2 zeros. 2 4s. I'll continue this down here. 1 and 2, 3, 4. 4 2.5s. And 2 4s. And 1 0. So all this stuff right here corresponds to Y. And all this stuff right here corresponds to the X. Okay? And after you're done with that, build all, hopefully it looks like that. I gotta do it now.
So 0, 5, 5, 18, 18, 23. Did you want to get that yet? Great. I was worried I didn't copy one of the points down correctly. Yeah, it'll complain if they don't have the right number. Like the number of y's have to equal the number of x's, of course. Yeah, and then do zoom extents to see the whole thing. Okay, so it should look something like that. It should look something like that. Okay, cool. All right, so let's go to extrude. So the extrusion is not on 2D, it's in 3D. So we have to go back up here to the 3D, highlight, right-click on geometry, and then go down to extrude. Okay, and then we're going to extrude this. You're going to highlight the thing you want to extrude, and you're going to extrude it up 3 microns, and then do build all. And so it should look like this. Okay. So next we want to do the next one. So we just did this. We extruded it. Now we're going to do this one. So we go back over to geometry, and we're going to put in. Oh wait. First, okay, yeah, this is going to be interesting. So we want our next geometry to line up with this face here. Okay, and extrude from this face that we're going to place out to here. And that's going to help us with our overlap. So I'll show you how to do that. So go back to your, let's see here. Yeah, go to your work plane, and then for this right here, go down and put face parallel in the plane type, because we want it to be, you want your plane to be parallel to some kind of face, right? And you click on this one right here. Oh, wait a minute, that's not right. Oh, what just happened? So, why do you keep doing that? Quick. So face parallel. This is not working as planned. So I have that. Geometry. Oh, I heard, yeah. This is supposed to be a new work plane. Yeah, my bad. Okay, so whatever you did, yeah. So go back to geometry and click on a new work plane, right? And then for this new work plane, then you go to face parallel. And then you click on your face. And it should look like that. You guys got that? Everybody? Good. Okay. Huh? Oh, and the last part? Probably got to hear because you get what I did. Oh, yeah. Yeah, so go back to that. And go to. Oh, wait, and then the error.
What are you recording?
He's recording the movie things. I need at least one to go all the way to the class, please.
Okay, so as you can see, that plane is intersecting that face right there, but we want to extend it out to here. Okay, so we're going to displace that. So go to offset right here, and then click in here negative 1.5 to offset it, right? If we do build all, it went that direction, but we don't want that direction. So you want to click on reverse normal direction, and then it'll put it where you want. And as you can see, is flush with this side right here. You guys see that? That's exactly what you want. And so we're going to build a geometry on this plane here, and then extrude it through that direction, through Y, the Y direction. Okay. Oh, yeah. So here's the difference between reverse. It gives you a different kind of positive sense, right? So if you click back and forth, it's like that. Like, are you going 1.5 microns this direction, or 1.5 microns out that direction? And that's what that does. It gives you a choice of what direction you want to go. Yeah. So yeah, if you want to do positive 1.5, you could have did like this, and then ended up with the same thing.
Which is now you got to say cut the other direction.
Yeah.
Straight the other way.
And as you can see, it's truly flush with this structure right there. Okay, so next, after you do that part, then what we want to do is go to our work plane now. In work plane 2, click on the work plane. And see this right here? Here's our new work plane. But as you can see, there's a projection of the other structure. And you get some choices. So this is coincident, here's intersection, and here's projection. I turned them all off. This is just a projection, right? So you know where it is. So if you want to start drawing, it'll make it easier to draw. But if you turn off projection and just turn on intersection, you may see this line right here and this line right here. So that's where this geometry intersects with your plane. And then this, turn off that and turn on this. And these are coincidence entities. And I'm not sure what that is. Okay, but anyway, so let's go to projection. That's the only one we need. Okay, and we will go to view the plane here. Oh, wait a minute. Yeah, so what we'll do here, right click on plane geometry, and then click on polygon. And we're going to do the polygon again to make this other structure. And I'll write it down again. Okay. So our new numbers are, there are going to be 1, 2, 3. There are 3 negative 1.5s. Okay. There are 1, 2, 3, 4. There are 4 0.5s. There are 4 negative 1.5 again. This time 4 instead of 3. And there are 4 1.5s. And last, we only have 3 over there. Here goes the last one, negative 1.5, one of those. That's going to be the x's. For the y's, no, copy and paste that to y's. Sorry about that. Yeah, okay, yeah. So here's the x's. I was looking at the wrong page. So copy and paste whatever you put here. Put that on the y line, on the x line. Okay, so for the x line, we have 111.5. We have 4 negative 6.3s. 4 of those. And then we have 4 positive 6.3s. Okay. Then we have 2 11.5s positive. And then 2 positive 6.5s. And 1 negative 11.5. And it should look like this without the fillets. When you build off. Anybody got lucky? Oh, wait a minute. Did you guys put this in vector form?
Yeah.
Okay, thank you. Glad you remembered that. Okay, negative 1.5 times 3.
Yeah, same.
Everybody's getting error? Let me check my my numbers, maybe I'm missing something. For the x's, like that. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4 this. 1, 2, 3, 4 that. 2 11.5s. 2 5 6.5s. I did miss something. There's supposed to be 2 things here before the negative 11.5. There's supposed to be 2 negative 6.5s. Yeah, this is a problem if you don't have like the right number at the top. Okay, so how's that? Still errors? You're right. Okay, great. Glad that was the only error. I have a little bug in mine. I'm trying to find out where that is. 1, 2, 1, 2, 1, 2, 3, 4. Ah, I didn't have a space between one of my things. Ah, there we go. Okay, so I finally caught up with the rest of you guys. So this is what it should look like. Okay, when you do build all, and then next we're going to go to fillets. So right click on plane geometry for that plane 2, and then go down to fillet, and it'll add that there. And what you can do is come over here. All the vertices are now dotted, and so you have to select which one you want. So you can do a select box and highlight these middle 2 like that, and then they appear over here. So 4 and 6 of mine are what those middle 2 are. And then for the radius of curvature is going to be 0.3 microns. Okay, then you do build all, and then you can see they made those curved. Okay, and next you go out to geometry again, and you do right click on geometry, and you want to extrude it. Okay, so we're going to do extrude, and this is the one you want right here. Oops, I'm click it again. So this is the one you want, and you want to extrude it for 4 microns. So this from this distance to over here is 4 microns, and so you say build all. -4 on mine. I must have changed my yeah. Okay, so it's either 4 or -4 microns, but it should look like this. Okay. Next, what you want to do is you want to do a Boolean. So you go to your geometry, and you go down to Boolean, and then you go to intersection. So this is where you get the part that you want, and you just click on the things you want to do intersections with. Both of those, you can do Control A, and you don't have to keep the interior boundaries. And then you can say build all. And so it should look like this once you get done. So how are we doing out there? Everybody got this? You can also go to Form Union and do build all there too. Okay, so now what we're going to do, this is something that you guys can do to try to ease some of your boundaries. You can name them, right? So these bottom boundaries right here, those things are connected to the substrate. So what we're going to do, we're going to call one of them connector 1, we're going to call another one connector 2, and then we're going to call both of them just connectors. So that means that you can select them, and they will appear in a drop-down list, and you can just select those, or you can just click on the boundary if you want to. So it's up to you, but you guys can select names to your boundaries, and sometimes that makes it a whole lot easier, especially when we start building your apps, your standalone apps. Okay, so let's go down to definitions, which is right here. That's definitions, and then you right-click on it, and then you go to where you want to go to? Oh, sections explicit. Okay, you want to explicitly define a section. Okay, and we could pick domain, but we're going to pick boundary. You can also pick an edge or a point and just name anything you want. So for this first boundary, this is the one we want right here. And we're going to call this connector 1. Okay? And as you see over here, it's now called connector 1 over here. Okay? Like if you expand this out right here, you can see that's called connector 1. Now we're going to do it again. Go to another explicit. And this one over here, go to domain. Pick your domain, which is this one right here. We'll call that connector 2. Okay? And then update it over here. And then go to sections, highlight it, choose another explicit, another name, and we're going to call this one connectors, them together, plural, with the S. And this time we're going to go to domain and select both 13 and 2. Okay? So those are just some names we're given. We gave those out of convenience. Okay, so once we're done with that, then we're going to add our material. We're going to make it copper. So you can go to home and you can go to, where's add material? Oh, right here, add material. Oh, it's already showing. So add material. Go down to choose MEMS. Go down to metals and then choose copper. And then click here, add component. So you can either double click on it or you can click it once and just say add component and it'll pop up over here. Okay, but one thing it doesn't have yet that you have to tell it is the relative permittivity. And for now, we're just going to call that 1 for our relative permittivity. Okay? Everybody got that? Huh?
I don't have the relative permittivity combined with that at all.
Oh, but you have all these other things?
Yeah.
Wow.
You go.
Let me see yours, what yours looks like.
You took copper and MEMS, right?
Added a bunch.
Oh, you did?
Yeah, so these added.
Oh, okay.
Okay, so that's relative permittivity, right? Also, let's go to material properties, and oh wow, it's already 1:45. So if some of you have to go, I understand that. If some of you could stay for like another 10 minutes, you can finish. I'll leave it up to you, but I'll put the document online. So if you can't stay, definitely do finish it today, or before we meet next lecture. So for those of you who can stay, we'll continue. So for this, go down to electromagnetic models. Okay. And then go down to linearized resistivity. That's this right here. Double click that. Click on that. And then choose reference resistivity, RO. Okay. And then say add material. This little plus sign is add to material. So these are some additional parameters that we're going to add to the material properties. And as you can see, once you click on add, these things are now appearing, but they're empty. So we have to tell it what it is. So the resistivity, we're going to key in as, I'll write it over here so you guys can see it. Okay, so for this right here, it's 1
0.72 E negative 8, and the units are ohms, all lowercase. So ohm times meters. Okay? It's times meters. For alpha, that's going to be 0.0039, and that is 1 over capital K, Kelvin. And for your T-ref, your reference temperature, that's going to be the 293 bracket Kelvin. Okay.
And be sure to get those in there with the units.
You still need units even though they already have units.
Oh, okay, that's cool. I don't think you need the units if they already have the units, because typically you want to put a unit in there if the unit is going to be different. If you do put the unit in there, it doesn't. It just overrides it with the same unit. So you'll be fine either way. Okay, so that's all done. Yeah, so that's the material. Okay. So the next thing we want to do is we want to go to the electric currents part. So let's go down to down here. This is electric currents. Okay, and for this we want to go to current conservation. Let me move this over a little bit. So go over here, and then we want to go down to here. The electrical conductivity, we want to change that to this linearized resistivity right here. So here's conductivity. I know we used sigma before to mean stress, but it's also used in electromagnetics as conductivity. Rho's the resistivity, alpha's the coefficient of thermal expansion. Here's the change in temperature right here. Okay. For now, what we'll do is, yeah.
If you didn't do this, what would you do instead? What's the default?
This expression right here is actually an approximation, right? It's actually much more nonlinear than this. So
Does it simplify the computation?
yeah, it definitely does that. And in fact, we're actually going to do a couple of things. So like for alpha, we'll do. I'll show you how to do two different studies. One with alpha being 0, and then another with alpha being material dependent. Because as the temperature increases, alpha changes, and you'll see the difference between the two. But this is a okay estimate for the type of currents we're experiencing. So for here, make alpha user defined. So initially we'll make it 0, and then we'll come back and change it to from the material itself. Okay. Now for the next thing, let's go over to electric currents, and then we're going to tell it which thing is the ground and which thing is receiving the voltage. So right click on it, select ground, and then go to here, and you can see what connectors you have. Remember, those are the ones that we labeled before: connector 1, connector 2, and connectors. So select connector 1, and that's going to be our ground. Let's go over to electric currents again, right click on it, and this time choose electric potential. and then go over here to select connector 2 for the electric potential. And since that's not 0, we'll put in what we chose, which was that's V0, and that was our 0.2 volts that we created in the parameter section. Okay, so now let's go over to the multiphysics section down here, and let's go to the thermal expansion part. Okay, now here what we'll do is we'll go down to model input right here, and for this we'll say user defined, and right here we'll put in our T external, and that's what we had a parameter that we had defined. Otherwise we could just type in the number. Now let's go up to the default model inputs. That's up here under parameters, and we'll go down to browse model inputs, and let's see, what we'll do here is we'll go to general, and what will we look at? We're looking for a volume reference material right here. So click on volume reference material, and then down here again put in your T external. Okay. Oh yeah, this right here.
Oh.
Yeah, sorry, that little. Yeah, so if you click on that, then all that other stuff drops down. This right here is a filter, so you can search for things in here too. Because a lot of times this is really highly populated with all kind of stuff. It's easier to find when you search for it. Okay, so now let's go to our heat transfer right here. We're almost done, everybody. So let's go to our initial values, and right here we'll put on our T0. That's our initial value. Remember, T0, that's where the sink is at the substrate. And then for heat flux, let's go to right click on this right here, and then add heat flux. And then what you want to do is just say all. So click on that and do Control A. Now this is going to be convective heat flux, so you want to change this to convective by clicking on that. For our H right here in this equation, that's going to be K, which we defined previously in the parameters. And for T external, just put RT external. Okay. Now let's go back out here again, and let's go right click on this, and now we're going to put our temperature in here. Click on temperature, and then in this field right here we put T0 for that. And then for our boundary conditions, remember we have these two to worry about, but we name those connectors. So you just have to click on connectors. And so these two things are going to be at temperature T0 throughout the entire process. So for the last physics, it's going to be our mechanical domain. So that is right here, solid, right here. And we have to tell it that these two things are fixed, where they're attached to the substrate. So right-click on solid mechanics, and then click on fixed constraint, and then say connectors plural. So those are both fixed. Now let's go to our mesh down here at the bottom. So right-click on mesh and do our free tetrahedral. But first go into size, and the kind of size we want is going to be finer. Not fine, but finer. And then say build all, and it'll build the mesh for you. It should look something like this. Okay? Now we can just do our study. So go down to study, click on that, and then click on equal compute. And then in a few seconds, hopefully, you got a result. So here's what this result looks like over here. And you can see that it bulges up. Okay, so remember, this over here is ground. This over here is at 0.2 volts. Both temperatures here on these bottom boundaries are at temperature T0. However, the temperature all throughout here is determined by the current going through here. What's being plotted is von Mises stress. Okay, so we're going to change that a little bit. So let's look at stress right here. Let's go to surface, and oh yeah, we're going to do two studies. So let's call this first one. Wait a minute. Okay, so yeah, so go back up to stress solid. Instead of labeling it stress solid, let's call it displacement study 1, or displacement 1. And we'll have another displacement 2 when we go back and change the alpha. Okay? And once you do that, it should change this to displacement 1. Then go down to surface right here. And you want to go to where do you want to go to? We're looking for something called replace expression. I lost my bearings here. So we go to results, displacement study.
So if you go back and run expression, then there's like there's a button up there.
Where do you see that?
You go to surface.
Uh-huh.
Click on that, and then there's the red-green arrow button.
Ah, yes. Thank you for that. Yeah, forgot about that. Yeah, thank you for that. Yeah, so if we go to that, go down to solid mechanics components. And then click on displacement, and then click on this one right here. So this is telling COMSOL to plot displacement instead of the stress. Okay, you can double click on that. And then you can say plot. And now, as you can see, the plot has now changed. Now it's plotting displacement. And in fact, if you click on this anywhere on this structure, it'll show you what the value is of that displacement right here. Tell you the coordinate and the value of that on the plot. Okay. Okay, so now we want to show what the temperature is. So let's go down to temperature right here. If you click on that, it'll show you what the temperature looks like. And you can click on it. It's hottest in the middle right here. So it's 1,000 degrees K. Over here it's like 323 K. In here, 323 exactly. Because remember, those were our boundaries that's connected to the substrate. And now let's go back to our electric currents right here and change our alpha. So go to currents, go to the current conservation 1, which is right here, and then scroll down to alpha, and then say firm material instead of user defined. And then go to this add study. Did it add it? Oh, add study. Oh, okay. So when we say add study, this new thing pops up. We say stationary, and then we click on add study. So this is going to be another simulation. And then we come over here and say compute. Okay, so this is what we get for that. And again, if you want to go down to the surface, click right here, and then you want to do the geometry again. You go to solid mechanics, you go to displacement, and you want to plot total displacement. Double click on that, and then you say plot it. Then you'll see what this is. So this is the displacement with alpha being chosen by the material. And if you click right here, you see that the deflection is not as high as the other one. If you click on this surface right here, you see that you get a different value for that. Okay? And of course, what you can do is here, you can call this displacement 2, just to make it clear. So displacement 1 is up here, displacement 2 is right there. And you can also look at the temperature as well, and those are also different. This value is, for temperature is 1038. Right here for temperature, we get like 705. A little different. Okay, but this is a more accurate model where that coefficient really depends on the material as it because it's a function of temperature. Okay. Anyway, that's all I have for today. Again, everything we did here, I hope that you can see that you can clearly apply it to this or this. The only difference is it has different geometry. That's it. Okay? But everything that we did here can be applied to those two things. But again, that's not until Thursday for that assignment. Okay, any questions? Okay. All right, thank you very much. Sorry we had the complicated technical thing in the beginning. so we went a little over, but glad you guys were able to stay.
Come on, Matt.
Yeah, that's totally my problem.
We're definitely going to report this over to IT. Right? So we have this problem on Tuesday. I mean, on next Thursday.